Welcome back to the deep dive. Today, we're unpacking a paper that gets right to the heart of what's arguably the biggest bottleneck in post-training right now.
It really is. The paper is Golden Goose, a simple trick to synthesize unlimited RLVR tasks from unverifiable internet text.
And that's from Ximing Liu and a team from NVIDIA, UW, and UCSD. So unlimited is a big claim, but they're tackling a very real problem: the scarcity of verifiable data for reinforcement learning.
Exactly. I mean, before we go any further, let's just quickly set the stage. When you look at the frontier models, DeepSeek, OpenAI's O-series, a huge part of their reasoning ability comes from RLVR.
Reinforcement learning with verifiable rewards.
Right. And the key word there is verifiable. You need a ground truth. You need a simple binary signal. Did the code pass the unit tests? Yes or no? Is the math answer correct? Yes or no?
Which is fantastic for, competitive programming problems or math Olympiads. But the whole premise of this paper is that we've basically hit a wall with that kind of data.
We've hit a data wall. That's the term they use. We've mined all the easy stuff. So you can keep training. You can throw more compute at it. But the model just plateaus.
Yeah.
It's not learning new reasoning. It's just getting better at that one specific format.
And all the while, this ocean of human knowledge, textbooks, forums, scientific papers is just sitting there, completely unusable for RL because it's not verifiable.
There's no unit test for a medical diagnosis, right?
Okay.
So Golden Goose is this pipeline that takes all that unstructured, unverifiable text and, well, it makes it verifiable.
Okay, so let's dig into the mechanism. They call it a simple trick, and it really hinges on one specific design choice. They're moving away from open-ended generation
and moving towards multiple choice questions, MCQs. That's the whole game.
So how does it work, step by step?
It starts with some raw text. Let's say it's a really good explanation on a forum or a key paragraph from a physics textbook. First, an LLM just cleans it up, extracts the important part.
Filters out the noise.
Exactly. Then, it identifies a really critical chunk of reasoning in that passage, a key step, and it just masks it out, replaces it with a mask token.
So far, that just sounds like fill-in-the-middle, standard stuff.
The setup is similar, but the task is completely different. That masked out text, that's your ground truth. The secret sauce is that they then use another LLM to generate a bunch of distractors.
So the model isn't trying to generate the missing piece, it's trying to pick the right one from a list.
Precisely. It turns an impossible to verify generation task into a trivially verifiable classification task. Did it pick option C? Yes. Reward is 1. No. Reward is 0. Simple.
That feels a bit counterintuitive. In the ML community, we usually think of open-ended generation as the harder, more valuable skill. Why force it into a multiple choice box?
It's a great question, and they actually tested this directly with an ablation study. They compared their MCQ format to a standard fill-in-the-mask version, and the open-ended version was a catastrophic failure. They describe it as behavioral collapse.
Behavioral collapse? What does that actually look like in practice?
Well, in one of their math data sets, the model got 0% accuracy on over 83% of the open-ended problems.
Wow, 0.
0. And it wasn't that the model was bad at math. It's that these RL-tuned models just refused to play by the rules of the task.
So instead of just filling in the blank, it tried to solve the whole problem from scratch again.
Exactly that. It would just ignore the context and start over. Or it would generate something that didn't syntactically fit. The output space is just too big, so the RL signal gets incredibly noisy. The verifier fails on formatting, not logic.
But the multiple choice format, it forces the model to actually engage with that one specific step. It puts up guardrails.
It constrains the problem. It forces the model to evaluate the logical consistency of that missing piece. And that gives you a clean, stable, dense reward signal that you just can't get otherwise with this kind of text.
So let's talk about the data they made with this. GooseReason-0.7. It's built from 2 really different kinds of sources.
Right. First, you have AOPS Instruct, which is from the Art of Problem Solving forums.
So high-level math, but messy. Full of slang and informal discussion.
Super messy. It's got proofs, debates. It's the kind of stuff that would completely break a standard math verifier. But the core reasoning is incredibly dense. Golden Goose just pulls out those reasoning steps and turns them into MCQs.
And the second source was Megascience.
Yeah, and this is maybe even more interesting. It's from, I think, nearly 12,000 university-level textbooks, Physics, biology, economics, computer science. This is where you get that deep conceptual multi-paragraph reasoning.
The paper uses a C programming example from this that I thought really made it click. It was about a malloc segmentation fault.
Oh yeah, the segfault one. It's a perfect illustration of where normal RLVR just fails. The problem is a user trying to allocate a 5 by 5 array and messing up the pointer logic.
A classic off by one pointer level error.
A classic. So the pipeline finds the correct line of code, the one with the right size of call, and it masks it. The distractors it generates are all plausible, syntactically valid C code. They just have the wrong pointer dereference or a slightly different cast.
So to get the right answer, the model can't just be pattern matching syntax. It has to actually understand what's happening with the memory allocation.
It has to have a mental model of computer science. And the beauty is, we didn't need a compiler. We didn't need to run a single thing in a sandbox. The verification is baked right into the task design.
Okay, so the pipeline is clever, the dataset is novel, but the big question is, does it actually scale? Does it move the needle on performance?
The results here are really strong. They took models that had already been trained to saturation on the standard ProRL datasets.
So models that had already hit that flat line we talked about.
Exactly. And when they mixed in the GooseReason data, those saturated models, they came back to life. They started improving again, setting new state-of-the-art results for 1.5B and 4B models across something like 15 different benchmarks.
Why, though? The paper introduces this metric, effective examples, to explain it.
Yes, and I think this is a really useful concept. In RL, you only get a useful gradient, a learning signal, when there's variance. If a model always gets a problem right or always gets it wrong, it learns nothing.
The task has to be in that Goldilocks zone. Not too easy, not too hard.
Precisely. Your pass rate needs to be somewhere between 0 and 1. And when they analyzed the standard ProRL data, they found only about 25% of the examples were actually effective for their models.
So 75% of the training steps were essentially wasted compute.
A massive amount of waste. But GooseReason, because it's sourced from this messy, complex human text, it naturally hits that sweet spot of difficulty way more often. Its effectiveness ratio was around 70%.
So you're just getting more bang for your buck on every training step.
You're getting a 13-fold increase in the total number of useful examples. That's what explains the learning curve reviving. You're just feeding the optimizer more gradients that actually matter.
This all sort of comes to a head in the cybersecurity case study. I thought this was the real proof of concept.
I totally agree. Because cybersecurity is a domain with basically no verifiable RL data to start with. There's no leak code for finding a 0-day. It's all just unstructured text analysis.
So what did they do?
They just pointed the Golden Goose pipeline at FineWeb, which is just a big scrape of the internet. They filtered for cybersecurity content and synthesized a brand new dataset, GooseReason-Cyber, from scratch.
No human labels, no handcrafted problems.
Nothing. And they trained a Qwen3 4B instruct model on it, a 4 billion parameter model, so pretty small by today's standards.
And a result.
That 4B model set a new state-of-the-art on cybersecurity benchmarks. It beat a 7 billion parameter model that was domain specialized and had a ton of extra fine-tuning.
That's a huge deal. The smaller, generalist model trained on this synthetic data beat the larger, specialized one.
It proves the point. The bottleneck isn't just model size. It's the availability of these verifiable reasoning signals during post-training. The 7B model might have read more, but the 4B model had practiced more, thanks to these synthetic tasks.
How does this compare to other methods like RLVE reinforcement learning with verifiable environments, the more traditional compiler and verifier approach?
RLVE is still king for its specific domain. If you look at the charts in the paper, for pure math, it's incredibly efficient. If you have a formal verifier, you should absolutely use it. But the paper shows it's also very brittle.
Brittle how?
It doesn't generalize. The models trained with RLVE actually got worse. They regressed on STEM and coding tasks that didn't fit neatly into the verifier's world.
So it's over-optimizing for the tool, not for the underlying reasoning.
Exactly. But Golden Goose gave robust improvements across math, code, and STEM all at once. It doesn't care about the subject because it's treating reasoning as a linguistic task, not a formal execution.
This gets to their scaling trend categories: diverge, outpace, and align. The diverge one seems like the most important finding.
Diverge is where the baseline model, trained on standard data, actually starts to get worse over time, while the GooseReason model keeps improving. They saw this on really hard benchmarks like code contests. The baseline was probably reward hacking the limited data it had.
And outpace is where they both improve, but Goose Reason is just much faster.
Right, and what's interesting is that align, where they performed about the same, was the least common outcome. So for most tasks, this new data fundamentally changes the training for the better. It just extends the scaling laws for reasoning.
So to wrap this up, the core contribution is a scalable, automated pipeline that turns the vast, messy internet into a source of verifiable training data.
It solves the data scarcity problem by just synthesizing a curriculum from text we already have.
And by shifting the task from open-ended generation to a constrained multiple-choice format, it creates a stable reward signal that revives saturated models.
We saw it enable a small model to outperform a larger, specialized one in a completely new domain just by processing raw web scrapes. It's a powerful idea.
The authors suggest this could extend to other data-scarce fields like law or medicine, which really gets you thinking.
It's the logical next step. You can't run a unit test on a legal brief or a medical chart, but you can use this method. You could mask the core legal reasoning in a court opinion and ask a model to pick it out from distractors based on dissenting arguments.
It fundamentally redefines what verifiable means for training. It's not about an objective, executable ground truth anymore.
Exactly. Verifiable just becomes internally consistent with a corpus of expert-generated text. If the model can consistently reconstruct an expert's reasoning against plausible alternatives, that itself becomes the reward signal. You're effectively bootstrapping a reasoning engine from the collected wisdom of an entire field.